Today I'd like to go over how to derive the maximum range for a projectile launched on level ground, and I'd also like to go over the idea of complementary angles. Some of you may have noticed that if you launch a projectile at 30 degrees, for example, it's going to have the same range if we ignore air resistance as if you launch it from 60 degrees. 60 degrees and 30 degrees are complementary angles. We'll see how that works too. Okay, first of all, we're talking level ground. Okay, so just a basic projectile problem on level ground. And what that means, if it's launched on level ground, is that the vertical displacement for the whole trip is 0. It starts out at the same level that it ends up. So delta y equals 0. So we're going to start with that and solve for t. So my first step here then would be to find the time with reference to our delta y equals 0, and with reference to Vy1, also theta, or V1 I should say, and then theta, and then also in terms of gravity g. I'll just leave that as 9.8, or we'll just write it as g, sorry. Okay, so we'll just use Galileo's second equation here in terms of the vertical. So I'll put delta y equals Vy1t plus 1/2 gt squared. Notice I'm using g instead of a here. That's specific for the acceleration due to gravity. That's a vertically oriented acceleration. Now remember that delta y is 0, so I could just substitute that in for this. That's the total displacement in the y direction. And if you remember, if we break this up into vertical and horizontal pieces, V1, we see that the vertical component would be V1 sine theta. So I can substitute V1 sine theta in for Vy1 here. So V1 sine theta, and then that's going to be times the t. And then now I think what I'll do is we'll remember that we'll define down as positive. Down is negative. V1 was positive here. So I'm going to make this minus 1/2 gt squared. Since this is positive pointing upward, the upward component, then g must be negative. So I'm going to make that a negative there. Okay, so if I just simplify it, I can divide both sides by t, and we end up with t is equal to 2 times V1 sine theta over g. And we'll keep that result and use it later. Okay, so now we have the time in terms of our y information. Okay, our vertical information. Now let's find the range in terms of our horizontal. So we're going to find the range delta x in terms of our using Galileo's equations again. So I'll just write out the second equation in terms of the horizontal. Delta x equals Vx1t, and now there's no acceleration, right? So that just be plus 0. That term just drops off. Okay, and I'll substitute in delta x, and for Vx1, if we think about our x component of our starting velocity, I can say that that would be equal to V1 cosine theta here instead of writing Vx1. And then that'll be, instead of writing t here, I will substitute this in for time. And so we'll end up with 2 V1 sine theta over g. That's just substituted in for time there. Okay, now we can go ahead and simplify this a little bit. So delta x would be equal to, now I have a V1 times V1 is V1 squared times 2 times the sine of theta times the cosine of theta over g. and so that would be kind of the result there. However, if you take a look, we see that there's right here there's a trig identity that you might remember. 2 sine theta cosine theta. Does anybody remember what that trig identity is? Trig identity. Well, 2 sine theta, oops, let me move this over. 2 sine theta cosine theta is equal to sine of 2 theta. So I could just replace that part with that. So that would give us, so delta x then would be equal to, delta x would be equal to v1 squared, and then instead of 2 sine theta cosine theta, I could write just sine 2 theta here. Sine 2 theta. And that's over g. So that's a little simpler. Okay? Now if we try subbing theta 1 and also 90 minus theta 1 and set them equal, we'll see if it's true. So delta x equals v1 squared sine 2 theta over g. Set that equal to v1 squared sine 2 times 90 minus theta over g. We have g's in the same spot. We'll multiply both sides by g. That drops off. Divide both sides by v1 squared. That drops off. And we're left with sine 2 theta equals sine 2 times the quantity 90 degrees minus theta. There goes the ceiling lights again. And that is true. Oops, that is true. Okay? So anyway, the net result is that that derivation tells us, just in summary, that if we have perfectly level ground and we shoot a projectile at, let's say, 20-degree angle, it's going to go, and we're assuming no air resistance, it's going to have a certain range, delta x. But if we shoot at the complementary angle, what would that be, 70 degrees? If we shoot that at its complementary angle, or 70 degrees, at the same velocity, v1, each time, so this one is 70 degrees, it's going to end up going higher and taking more time in the air, but it's going to land in the same spot. I didn't draw that very symmetrically. That parabola should be symmetrical, the first half equaling the second half. So the range will be the same, whether you shoot it at a 20 degree or 70 degree, and for other complementary angles also. Thanks a lot.